In this video, we're going to talk about the first law of thermodynamics and how it relates to internal energy, heat, and work. So what is the basic idea behind the first law of thermodynamics? The gist of it is this: energy cannot be created or destroyed. It can simply be transferred from one place to another. So let's say if we have a system and everything outside of it is the surroundings. Energy can flow into or out of the system, and there's two ways in which energy can do so, and that is through heat and work. So if heat flows into the system gains energy, and that energy is known as the internal energy of the system, represented by the symbol capital U. Now, the surroundings can do work on a system. So those are the two ways in which a system can increase its internal energy. It's by the transfer of heat energy into the system, or if the surroundings perform work on a system. So let's say if the surroundings perform 300 joules on a system. That means the system's internal energy goes up by 300. So the change is positive. So delta U increases. The energy of the surroundings, however, has to decrease by 300. And so energy is not created or destroyed. It's simply transferred from one place to another. The system didn't just get the 300 joules from nowhere. That 300 joules of energy came from somewhere. It came from the surroundings. A good way to illustrate this is to use money. So let's say if you decide to sell a laptop for $500. Someone will buy the laptop for $500. Let's say if someone does buy it. Your bank account will increase by 500, but that person's bank account will decrease by 500. And so the money just doesn't come from nowhere. It just doesn't just magically appears. It comes from somewhere. So in order for you to gain 500, someone else has to lose 500. Now granted, the government could print more money if they wanted to, but in a practical sense, in everyday life, when someone gains money, someone has to lose money. And so in that sense, within that transaction, money is not created or destroyed. It's simply transferred from one place to another. And energy follows that same principle. Unless you're God, energy cannot be created or destroyed, as far as we know. But in today's world, under practical conditions, energy is simply transferred from one place to another. So in our example, if the system gains 300 joules of energy, that means the surroundings loses 300 joules of energy. If the system loses 500 joules of energy, the surroundings have to gain 500 joules of energy. And in that sense, within that practical area, energy is not created or destroyed. Thus, we have the first law of thermodynamics. Now, there's three types of systems that you want to be familiar with. The first one is an open system. The second is a closed system. And the third is an isolated system. So in an open system, matter can enter into an open system. So oxygen from the air can go inside of it, and also heat energy can flow into an open system. So matter and energy can be transferred into and out of an open system. Now, in a closed system, matter cannot flow into it. So oxygen it can't go inside of a closed system. However, energy can still flow into a closed system. So in a closed system, only energy can go into and out of a closed system, but matter cannot. In an isolated system, energy or matter cannot enter or leave an isolated system. So the mass within an isolated system is fixed. It doesn't change. And the total energy of an isolated system also doesn't change because no energy can flow into it or out of it. The equation for the change in the internal energy of a system is Q plus W. And this is the equation that you'll see in a typical chemistry textbook. Q represents the heat energy that flows into or out of the system, and W represents the work. Now in physics, the equation is a bit different. In a physics textbook, you'll see delta U is equal to Q minus W. Now you might be wondering, why is it different? Why is it not the same? And the reason for that is the point of view taken by the scientists. In chemistry, we take the system's point of view. In physics, engineers take the viewpoint of the surroundings. So in chemistry, W is negative when work is done by the system. Anytime work is done by the system has to expend energy to do work, and so the internal energy of the system decreases. Imagine if you're going to the gym to work out, and as you lift weights, your body is burning energy. The internal energy of your body decreases as you burn calories. And so work is being done by the system. That is, you're the system, you're doing the work. And the surroundings might be the weights that you're lifting. So as you burn calories to lift up a weight from, let's say, the ground to an elevated position, the potential energy of that weight increases. But the internal energy of your body decreases because you're burning calories, you're losing weight. In this case, whenever W is negative, work is done by the system in the case of chemistry. And when W is positive, work is done on the system. Now in physics, it's different. We take the surroundings point of view in physics. So W is negative when work is done on the system. And W is positive when work is done by the system. So let's analyze these two cases when work is done by the system. So in chemistry, when work is done by the system, as we said before, the internal energy decreases. And because the energy of the system is decreasing, work is negative. Remember, we're taking the viewpoint of the system. In physics, we want to take the viewpoint of the surroundings. So when work is done by the system, the internal energy of the system still decreases. However, we say W is positive because the surroundings is gaining energy. We're taking the viewpoint of the surroundings. And so since the surroundings gain energy, W is positive. In the case of chemistry, when work is done by the system loses energy, so we say W is negative. And so it's the viewpoint. And that's why the equations are a bit different. In chemistry, we take the viewpoint of the system, but in physics, we take the viewpoint on the surroundings. So when work is done by the system loses energy, the surroundings gain energy. So if you're focused on the surroundings, then W is positive because the energy of the surroundings go up. If you focus on the system loses energy when work is done by the system, and so W is negative. But in this video, I'm going to take the system's perspective. So going back to this equation, delta U is Q plus W. You need to know that Q is positive whenever the system, meaning the reactants and the products, absorb heat energy. So anytime heat flows into the system, heat energy is absorbed by the system, so Q is positive. This is an endothermic process whenever heat energy is absorbed. Now Q is negative whenever the system releases heat energy. And so heat energy flows out of the system into the surroundings. And so this is an exothermic process. So anytime heat energy is released, it's exothermic. And when heat energy is absorbed by the system, it's endothermic. So for an exothermic process, Q is negative, and for an endothermic process, Q is positive. And as was mentioned before, W is positive when work is done on the system. This is in chemistry. And W is negative whenever work is done by the system. So you need to be familiar with the sign conventions if you're going to use this equation. So in another video, I'm going to give you some practice problems on calculating the change in internal energy using heat and work.